Hello everyone, welcome to Maths and Tech, your home of value. Today we're going to cover matrix algebra. So what is a matrix? So this is a rectangular array of elements, that is numbers or letters. So you have an example there, and I think I must mention that this has to be enclosed in the square brackets, as you can see. Right, so we have a matrix there, 3, 4, 2, 7, A, B, and C, D. So those are two matrices. Okay, so the numbers and the letters in the array are referred to as elements or entries or components. So remember, you said a matrix is a rectangular array of elements. All right, so now these elements or these numbers, so each number, for example number 3 in the first matrix is an element. Okay, so for this lesson we are going to be referring to them mostly as elements. In the other array we have, say, B. So B is an element in that matrix. Okay, so we've given a good example there. They are very well illustrated there, so this should help you up in your revision as we move on. So I'll be moving very fast because you can always pause and maybe try to figure out what we said about the matrices as we go on. So the next one is the size and the dimension. So when you're talking about the size and the dimension of a matrix, you always start with the rows and then you go to the columns. So remember, matrices are rectangular in nature. That means they'll have the rows and they'll have the columns always. So for example, we have that one, 3, 4, 2, 7. Now that is a matrix of order or of size 2 by 2. Why is it 2 by 2? The first 2 is for rows, right? The first 2 is for rows, this one, and the other one is for columns. So 2 by 2 meaning the first one 2 rows, the other one 2 columns. The next one we have 3 by 3, as you can see there. So 3 rows, 3 columns. So as far as matrices are concerned, we'll always start with rows followed by columns. So rows always take precedent when you're regarding or talking about matrices. Okay, you can see it's well illustrated there. I took my time to actually do this infographic so you to just see and have an easy time in this. So the next thing is naming the elements in a matrix. So we have all these different kinds of elements or different elements in a particular matrix. So how do we name them? How do we name the position of each element? Okay, so now we want to identify the elements in a given matrix. So for example, we have a matrix here, A, B, C, D. All right, so in what position is B? So the same thing applies. You start with the rows, then you go to the columns. So for example, position B is in the first row and the second column. That's why it's B12. So 1, 2 in this case is representative of the position, meaning the first row, the second column. Okay, so this is the first row, this is the second column. The first column is here, the second column, the first row, the second row. Okay, so these are rows. Of course, up here we have the columns. All right, so it's very important for you to actually get that. Very important. Okay, and I've of course taken my time to actually, so you can even post the video and probably just go through these elements here, so for you to know which row and which column our matrices or our elements are in. Okay, so let's go to the next part. Of course, there is also this. So when we take a letter A, this just denotes the matrices. Of course, assuming you have 10 matrices, how do you distinguish between one matrix and the other? We give them letters. Okay, that's why you can see A there. So A there is representative of that matrix. You can have another matrix B, another matrix C, another matrix D, and so on. All right, so A is just representing the entire matrix for you to distinguish between one matrix and the other. So when we say A23 means matrix A position 2, 3. So position 2, 3 in this case is second row third column, which is of course 8. Okay, this is in the second row, the third column. That's why you can see 8, 2, 3. Right? Of course, and you can also try the others and see whether you're actually getting the gist of this. So you can also try position A33, which will of course give you 9, and see whether you can actually get 9, which is the third column, the third row and the third column. Excuse me. Okay, so when you go to A31, meaning the third row, the first column, okay, the third row, the first column, which is of course 0. So you should be able to do that by now, and if you can't, you can just pause the video and try again, or replay the video for you to be able to do this, because it's important. Then the next thing is the types of matrices. As you can see, they are very well illustrated here. So what we have, number one, a column matrix. So this is a matrix consisting of a single column. So now when you have a matrix with only one column, that is referred to as a column matrix, and this is very well illustrated there. So the next one is a row matrix. So these are matrices consisting of single row of elements, like you can see illustrated right there very nicely. Then we have a square matrix. So a matrix C is said to be a square matrix when it has the same number of rows as the columns. So e.g., you can see an example there, C. Okay, so C has how many rows? The first row, the second one, and the third one. So there are 3 rows. And then we have columns, the first column, the second column, the third column. Alright, so 3 rows, 3 columns. So that qualifies to be a square matrix. If we had 2 rows, 2 columns, again still that's a square matrix. Okay, now let's go to diagonal matrix. So this is a square matrix with zeros everywhere in the matrix except in the main or the diagonal matrix. So that tells we have a main diagonal. Which is the main diagonal? Of course, top left to bottom right. Okay, top left to bottom right. That is a principal or a main diagonal. Okay, so you may ask, what is the name of the other diagonal? Because of course, when you have a rectangle, we have 2 diagonals. Okay, one from left to bottom, top left to bottom right, another one from top right to bottom left. So now that is called the alternate diagonal. So I just mean this is the one that I'm talking about, this one. This is called the alternate diagonal. So in this case, we are talking about the main diagonal. So a diagonal matrix is a square matrix with zeros everywhere except in the main diagonal. So you can see in a matrix there, the main diagonal has 1, 7, 9, and all other elements are zeros. So that's a diagonal matrix. Then we have the identity matrix, which we'll actually be using quite a lot as we go on in this topic. So this is a diagonal matrix in which all the elements in the principal diagonal are 1 and all other elements are zeros. Okay, so this is actually equivalent to 1 when you're referring or in regard to numbers. Okay, you're going to see that later as we move on. But so the identity matrix, 1 is a diagonal matrix, 2 it has to be a square matrix. All right, as you can see, then all the elements in the main diagonal, as you can see, we say the main diagonal is from top left to bottom right. You can see all of them are 1, 1, 1, 1. Okay, so that's an identity matrix. The other one is a 0 or null matrix. So these are matrices whose elements are equal to 0. So when you have a matrix E, which all the elements, remember we've talked about what elements are equal to 0, that's a null matrix. Then we'll very quickly go to a submatrix. So you can form a submatrix from any matrix. So how do you form a submatrix? The submatrix of a matrix A is another matrix obtained from A by deleting selected rows and or columns of a matrix A. So let's assume our matrix A, I'll just put it up here. Matrix A is 4, 2, 3, 1, 4, 0, and 2, 3, 1. So let's assume that this is matrix A. So if you want to form a sub-matrix of this matrix, say you just need either to delete one column or two of them, or a row. You either delete a column or you delete a row, and that will give you a sub-matrix of the original matrix. So a good example, let's delete the first row in that matrix. So if we delete 4, 2, and 1, we are going to remain with 1, 4, 0, 2, 3, 1. So this is now a sub-matrix of the original matrix. Now what if we delete that first column, I mean row, and then we also delete the first column, so this one? We are again going to have a sub-matrix of 4031, which is also a sub-matrix of the original matrix. So that's how you form sub-matrices, right? I hope that sank in. Good. Let's also go to other types of matrices. So we have another one called triangular matrix, and we have a lower triangular and of course an upper triangular. So what is a lower triangular? So all the elements above the main diagonal elements are 0. So remember we've talked about the diagonal elements, or above the diagonal elements. So we're saying all elements above the main diagonal. So we have said what the main diagonal is, of course, from top left to bottom right. So you can see we have 1, 7, 9. That's our main diagonal. So all the elements up or upper side are 0. All the others are what? Are other numbers. So you can see when all the elements above the main diagonal are 0, that's a lower triangular. But now the opposite is true. The upper triangular is when all the elements below the main diagonal elements are 0. Very well illustrated. I even took time to just draw that, to show this with some infographics, and did a bit of orange for you to just become aware of this, or to just illustrate nicely for you to understand. So this is called an upper triangular matrix. Okay, very easy. Then we go to the next one, which is a scalar matrix. So a diagonal matrix whose main diagonal elements are equal to the same scalar matrix, to the same scalar. A scalar is defined as a single number or a constant. Okay, so for example, if a scalar is any single number, for example, if you have 10, you have 7, you have 4, you have 2, all those are scalars. Okay, so when you have the main diagonal, remember when we had the main diagonal being 1, 1, 1, that was referred to as an identity matrix. Okay, here, right here. But now we are having a situation where we have a scalar quantity, and a scalar quantity, we have said, can be any single number or constant. Okay, so if you have 6, 6, 6, so assuming you have 5, 4, 4, 4, is that a scalar matrix? Of course the answer is no, because you have to have all the elements on the main diagonal being the same scalar quantity. So if they are not, that is not a scalar matrix. Then we go to the next one, which is the transpose of a matrix. Or just before we go to the transpose, let's move on to symmetric matrix. So a square matrix is symmetric if it is equal to the transpose. Okay, before long we are going to look at what a transpose of a matrix is. So for now, just know that a symmetric matrix is equal, the matrix is equal to the transpose. Okay, so this is also, we can go further and say the lower triangle is a mirror image of the upper triangle along the main diagonal. So what do we mean? Now this is the main diagonal here. I think we have already talked about that. You can see if we draw a line there, all the elements correspond and they match. So 0 matches with 0, 2 matches with 2, 4 matches with 4. So that's why it qualifies to be a what? A symmetric matrix. So symmetry is almost like a property. So you can see, you can also put it like that. So let's also go to now something else we call the transpose of a matrix. We have just seen it right there at the symmetric matrices. So what is a transpose of a matrix? Okay, what is a transpose of a matrix? So the transpose of a matrix, denoted by A of t, A raised to power t, of course t being transpose, of an m times n. When we say m times n, m represents the rows, n represents the columns. Again, of matrix A is the n times m. They have just interchanged those letters there. Matrix A to power T obtained by interchanging the rows and the columns of A. So all this is just simply to say what? When you interchange, you make the columns to become rows or the rows to become columns. That is now what we call the transpose of a matrix. Now, I'll quickly give an example. Let me go right here where I have space so that I'm able to explain this. I just want to explain this. So, assuming I have a matrix A, which is 1, 2, 3, 4. Okay, so this is a matrix. This is a 2 by 2 matrix, and I want to get AT, which is A transpose. What do? I'll just change the first row to become column and the second row to become a column. So what do? You just write 1, which is our first row, and then 3 going down. So we have changed the first row to be a column. Then you go to the second row, also convert it to become a column. So again, you'll have 2, 4. Very easy. So that is the transpose of what? Matrix A. So you can change rows to become columns or columns into rows. It doesn't matter. So let's now change the columns into rows and see whether you get the same. All right. So our first column is 1, 2. So let's change 1, 2 to become a row. So when we change 1, 2, you write it now 1, 2, the first row. And then the second column on A is 3, 4. So again, we change it to become a row. So this will be 3, 4. Again, we have the same answer. Okay? Sorry, excuse me. So that becomes the transpose of that matrix. Very, very easy, as you can see. Okay, so just a minute. So let me go back right up to where we were. Good. We are done with the transpose of a matrix. Let's now go to the equal matrix. Okay, so matrix A and B are equal if and only if they are identical. That is, if they both have the same number of rows and columns, and the elements in the corresponding locations in the two matrices should be the same. That is, Aij is equals to Bij for all I and j. So I and j here are to represent, of course, the rows and j the columns. Again, we've said it's very important for you to see that the elements in the corresponding locations must be the same. Okay, the elements in the corresponding locations must be the same. So what do we mean? We have already looked at the corresponding locations here. So for example, in location 1, 2, okay, for our first matrix, which element do we have on position 1, 2 in our first element? 1, 2 meaning the first row, the second column. Okay, that of course is 4. Okay, of course this is 4 here on position 1, 2. On our other matrix, the same 1, 2, we also have 4. Okay, so if you do that for all the other elements, you'll find that they are the same. Okay, all of them. So for every corresponding position, we have similar elements. That's the only time we say that the matrices are equal. All right. So I hope that has sunk in. Well, now in our next lesson, we are going to look at now operation on matrices. Okay, that's what we are going to look at. So see you in our next lesson. I hope this class was fun. So see you in the next one.